Like I said, I got a lot of these. There's a lot of benefits. Low energy consumption. I can run 1 or 100 boxes on the same size pump. That's a huge savings on electricity. That you can, all that electric, you can run into something else. Let's see, and that's an experiment there. That's, by the way, Nick there is 6'8". Okay, so that's not as small of a box as you'd think. That's just an abnormally large human being. And then Nick did a great job as an intern, and we moved him. I guess he started his own business actually after he got done. Let's see. Accepts a mixed waste stream. We already talked about that. It can be automated for monitor, command, and control, or auto siphon flushing and then leading all that material to dewatering bags. And I like dewatering bags. That's what we do now on our mine drainage sites, because then you're not dumping that sludge into another pond and then slowly filling up that pond. If you can dewater it, then you have the opportunity to sell that material and move that on. And then now, if you can sell the material, you've got ROI. That's return on investment. That pays for the system itself. So let's see. And then specifically Martian stuff, mass anchors for surface domes instead of permafrost. You know, we were looking up what's the minimum temperature that water stays liquid. And James, who couldn't make it tonight, he's found out it's -21 Celsius. So we're looking at, what is it, like -10 or something, and that gives us a further buffer space of thermal energy that we can work with on Mars, whether it be fighting conductive loss for the ground or transferring energy where we don't have to worry about the convective loss because it's such a thin atmosphere on Mars. Oh, okay. Well, there you go. Just talked about that. Decentralized infrastructure. If you can have, right now we've got 3 wastewater treatment facilities in all of Altoona, and they cost on orders of hundreds of millions of dollars, versus everybody investing in their own decentralized infrastructure, so that when a pipe breaks or something goes down, it is the same thing as like having solar panels versus a coal-fired power plant. When the power plant goes down, I go downstairs and I'll just throw a switch. Well, I got my own solar. I got my own electric. Not here yet, but I also do personally work with a solar company. Shout out to Groundhog Solar here in Pennsylvania. So decentralizing that infrastructure, and especially on Mars. I mean, here we can get away with it because we're so connected and we can just walk outside. On Mars, you're screwed. If everything goes down, you have to have decentralized infrastructure as much as possible. And then potentially long-term engines of biogeomechachemoelectric terraforming or paraterraforming. And the idea being that if you eventually process enough regolith with, say, billions of boxes, billions of wetlands, at what point do you start developing enough of an atmosphere that you can start warming the planet itself? And that would be entirely predicated on making sure that the atmosphere you're producing isn't getting just wiped away like it's already occurred. And that but those are physical then manifestations of things that you can do up in space. It's just big, real big, but it's not undoable. That's the thing. Like we know how to do this. We lack the willpower and the experience and the funding. But where the funding always comes from willpower. So willpower and experience, I think that's the only thing really stopping us from taking a serious crack at some of these issues, or some of these opportunities, I should say. Because there's always problems. There's things that you want to think about. Like, I mean, I don't want to oversell a rosy picture of this. There are some things that have to be overcome. But now with the technology we have available today, and I'm not even saying a couple years ago, but today, they're not really problems anymore. Some of them are stupid simple. Some of them are biggies though. So the biggest problem is if a niche caves, fails, whatever, it gets a super high dose of GRC, which, the cosmic rays, and it just totally nukes a cell. It can be reconstituted through either, if you have other ice blocks that you brought from Earth, or CRISPR-Cas9. Already talked about that in the very beginning. So that there's ways that when it crashes, you can bring it back. It's okay. But beforehand, that would have been the killer. Nobody would have ever have taken this seriously if not for the fact that we could regrow microbes up there. Otherwise, it's, you know, as rosy as and as much as I love it, without that, I got to say, I don't think it would ever work. But the solutions, like I said, initial transport, frozen water or wetland samples, Physmec, small blocks of ice shielded by more ice to protect against the GCR, and Phys electric software, so CRISPR-Cas9. Okay, another problem. We talked about this, waterways less on Mars. So hypothetically, move slower through a Sowb, and that's a self-organizing wetland bioreactor, or pipe under gravity only flow, no pressure. Nothing pushing behind it. This can lead to more clogging, and could. There's things you can clean outs. There's very simple engineering things that you can do to stop those issues from coming up. That's not even getting into like robots, like going through pipes and pulling clogs. I mean, you know, simple things. Let's see, and you might have much longer residence times under the same flow rates that we would expect here on Earth. And solutions: greater downward angle on the pipes, rise over run, bigger pipes. I mean, ovular instead of round. On Earth, Sowbs are placed level to maintain freeboard. You can just increase the freeboard. Freeboard, by the way, is like if here's the water level and here's the top of the box, that distance in between those two, that's your freeboard. If you want more freeboard, just go to greater space. And that way, if there's a flux or if it really starts sloshing around in there, it doesn't go up over the side, you know? That's freeboard. Let's see, you could also decrease the loading of chemical biological oxygen demand through dilution. You could have Venturis dumping more O2 that's pulling directly out of the grow habs, so the permacyclers, where you've got oxygen produced through plants. Gas injection. Every one of the boxes comes with a gas injection system. Decrease the pressure on sealed Sowbs with one-way valves, increase flow rate temporarily. So just, you know, your sealed boxes, just put some pressure onto it, you know, and inject pressure, or conversely pull a vacuum. If you're trying to off gas. So that's another thing that we're thinking may be very useful for the perchlorate step, that as you are reducing the perchlorate and driving off that oxygen is going to be in solution up to the maximum capability of the saturation, depending on water temperature. And if you want to drive it off faster, we're just thinking pull a vacuum on it. And it'd be like giving the water the bends, and it's just pulling that O2 straight off while leaving all the other chemical, or the salts in place. So, you know, Piltman, no, shoot, what's the big singular, it'll come to me. There's a piston, and it just pulls one single piston. It's a really huge engine. It'll come to me later afterwards, I'm sure. Okay, also gravity related bioremediation, and this is also a biggie, favors anaerobic niches and slower flow rates, and it's load dependent. Changing the arrangement, redox couplets. If anybody's ever played Norbit from way back in the day, you know, there's that little guy that jumps down on all this ladder of steps that increases and increases. Think of that. And if you're starting aerobic at the top and methane at the bottom, you need, say, for one aerobic box, you would need 16 methane boxes to be able to get the same energy at the same flow rate moving through the system, because the ATP available for aerobic respiration is 32. Methane is 4. So you got a 16 or eight times different. So it's, 8 to 1, one to the other. But if you do it that way, so in a passive flow, direct flow through system, if you have one box at the top taking care of the aerobic, and take care of your nitrogen, and then your selenium and sulfur, and then your methane, and that's that step. But then you can have a direct flow rate with a static system and no change in moving parts, and then you're just splitting the flow and however many flows or however many boxes, step by step by step by step, all the way down through the system. So that's kind of how you want to envision it. So that's one physical or mechanical thing that you could do that's simple, doesn't require any more energy. Let's see, steel support structures. I'm not really sure why I've got that in there, but you got iron and manganese making steel. That's ISRU. So, you know, supporting lots and lots and lots of weight. If we are going to be supporting 30 feet of water above the domes to make sure the domes don't blow off, Who cares? We can make steel. We can make damn good steel while we're up there. And because we have biology doing most of the work, all that smelting energy from all those nuke reactors that we would otherwise have been using to make products and process water, we can dump straight into just making steel. So we have so much more energy available to be able to now make the things that we know we're going to need to be able to terraform the entire, well, however much of Mars is feasible over time. And this, by the way, all goes directly back to the work that Dr. Dan Tompkins did. Dan's on the line right now with our settling space entry for the Mars Society 1 million person design or civilization design contest. So this is all coming directly off of what we'd already pulled together. You could do smaller cells, blah, 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 screen out larger material to be saved for later, like woody or pulpy matter, just some basic pre-filtration. You know, surface area increases CBOD availability. Just like, you know, are you going to have a faster rush by pureeing your food and then sucking it down versus eating it? Where, you know, what's the faster availability? You know, is it protein, like you're eating a handful of like walnuts or something like that, versus a candy bar that's just straight sugar, you know, which is going to be more easily available. So playing with the recipes as they move through these systems will definitely play out into the efficiency of the system as well as the purity of the byproducts through the system. You know, did you have such a good methane digester that not only did you get the hydrogen sulfide out, but the CO2 content is less than 10%, you know? That's a good methane digester right there. That's what you're looking for, and that's determined in part on the products and the structure of the box or of that bioreactor itself. Okay, sweet, moving right along here. Okay, so the primary functions. I didn't get anywhere near this far in LA. The primary function is a thing that only a Sowb can do. Once again, 90% of the work, talked about all the rest of that stuff. Secondary functions would be another complementary technology that can meet the same needs and products at the same efficiencies. And having more things, great, better redundancy, more redundancy. The long-term, the biological will be more stable, but nothing is foolproof. You'll always need a backup. Combination of couplets and varying loads. And then the tertiary functions that a wetland or a bioreactor may be capable of doing can be used as a backup to other prime or second order functions, but not very efficient. Lower energy yielding redox couplets under low loading used as low power redundancy. This would be like you've got a lot of extra waste material and you just run them through a bunch of Winogradzki columns for, say, just reharvesting a little bit of energy before you run it through other mechanical systems to get yourself back to purity. Whether it be potable water, a useful industrial water, gray water levels to send back to, say, your agricultural habitats. Those are, and Phil obviously can talk a lot about this because the biodome that they're working on right now, this is the big thing. Like, where does this go to this, goes to this, goes to this, goes to this, and then out. So that's, they spent an enormous amount of time designing the rainwater catchment. The entire thing is a giant swamp cooler. Using evapotranspiration and just evaporation, evaporative cooling. And actually, Phil, we should have you do an entire thing on that one of these next webinars, come to think of it. Okay, let's see. Already talked about some more or prime uses of the Sowbs: clean methane, CBOD direct as O2 for agricultural spaces, carbon dioxide enrichment, and agricultural habs. They can also help to take up the excess pressure that would be required. I think it's only like 0.5 or 0.3% of an atmosphere, one atmosphere is required to keep plants alive. Whereas we need like minimum, I forget, 1.5 or 2. I forget. We'll ask Stelly here a little bit later. But Winogradzki bioelectric generation, attenuation, and essentially all the boxes are, as opposed to a Winogradzki column that is vertical, and you can see vertical stratification, the boxes are that just taken on the side, and then allowing for gravity to allow for volatilization and off-gassing, and that's That's the key. It's still they're both doing the same thing, but instead of a vertical distillation tower, it's a horizontal distillation system that then can spread out multiply, depending on the redox couplets, for as many boxes as you need to get through the entire thing. Hospital wastewater, antibiotic, and pharmaceutical degradation. We did a paper with Dr. Bill Burgos from Penn State showing the degradation of antibiotics and pharmaceuticals. Some, not all. Some it did a great job on. Others it didn't even touch. So it's not a panacea here. I mean, you're still going to need other technologies to get your wastewater totally clean if you're recycling all your sieve hab and all your black water, because that's where most of those pharmaceuticals and antibiotics are going to be. They're going to be in feces and urine coming out of you and I, and other things as well. Let's see. Prime uses of biogeochemical cycling. It's just some of the things that are going to be moving through the system. Products of solids. Yep, we talked about that. Perchlorate. I did talk a little bit about this earlier. So just perchlorate reduction yielding chloride and dissolved oxygen, or DO. Let's see, waste plant matter and standard wetlands provide surface area. So this is where everything left over from the agricultural habs are like all the hemp, the lignans and whatnot, silage, corn stalks, if we're, coconut husks left over. That's what would be going and providing the surface area for these wetland embodiments. So it's still organic in nature. Because it's easy, because then you can stir it around and bubble it up and break it free. It's so much easier to clean than say like plastic, which is damn near impossible to clean if you have like a plastic matrix. I've worked with it before. For certain things, it's great. Other things, it's just way too expensive, breaks down into microplastics. It's got its uses. Ammonia newts may be needed depending on nitrogen availability and the local regolith. This once again goes back to just being able to provide the metabolites and the things that you're going to need to you're growing bugs. It's like growing plants. If you don't provide them everything, they're not going to get to where they need to be. Chloride continued. I kind of already talked about this. Yeah. Here's a permacycler. This is actually sitting just on the other side right there. And that was a wetland in a box conjoined to a semi-sealed, as well as I could make it sealed with the intern, a photic reactor. I ended up, it chewed up about 1.2 kilowatts of energy, about $40 a month. But, it was loud. The air compressor that was pulling the oxygen from the top, and actually you can see part of the manifold system underneath there coming back in. And then so it's bubbling through each one of those cells and then breaking up the BOD and the COD. And then all that oxygen goes back up through the system. And that's actually a little piezoelectric cooler where water would capture on that. And it's a dehumidifier. It needs to be about 4 or 5 times stronger than that one in particular. But it worked, just need better scaling, and then goes back up through and it keeps cycling. That's how it cycles the oxygen. And when you turn the compressor off, I've got a CO2 monitor here, and there's one on the inside. And I got the CO2 down in here. It was started at about 380, 400 parts per million. I got it down to 20, which means there was nothing but oxygen left over in there. If I'd lit a match in there, it would have blown the damn thing up. And that would be a really fun experiment for the future, just not with this one in particular, something where, you don't really care about it. Not something that costs us $5,000 and hundreds of hours worth of time and research. Let's see. So that's the permacycler. Let's see. Okay. And then the Agora. So going to larger scale, these boxes, because they can do anything that water is involved with, they have an ability, depending on what the loading is and what the pollutants or the impacts are, to self-organize and then self-select and self-organize for a wetland environment that can clean hundreds of thousands of gallons of water a day. And in humanitarian disaster relief, now what isn't picture? So you've got a shipping container, and you've got boxes, and you've got water coming in, water coming out. And this is basically, in this function, it's set up like a permacycler to grow as many microgreens as you can. So, people may not be dying. They're going to be hungry, but they won't be malnourished. That's the big thing. Just keep them alive and make sure that they at least have the basics that they would, basic nutritional things, so they don't, they're not all of those other not endemic, chronic chronic ailments that we see in a lot of people displaced throughout the world or experiencing. And then all of this, it doesn't show it right here, but all of this is packed with 60 or 80 kilowatts of solar panels on top of all of it. I just can't show the solar panels on top of all this, or else you wouldn't really be seeing anything but solar panels. And those would be provided by Groundhog Solar, and they all come packed in the boxes themselves. And then you just unpack everything and put the whole thing together in about 2 days. It's all designed 1 to 2 days for rapid response. Now, it should be said that the wetland environment that develops, depending on what the impacts are, it'll either start working immediately, or it may take a month before it really, like say you got a lot of manganese oxide or manganese in your water. Generally not something that you're going to come across, just using it as an example. But it usually takes about a month to get the biomass in that system up high enough to start being able to remove useful levels of manganese. But then when you do, you're doing it at a lower pH, and they're doing it at 50 to 150 times greater treatment density. So sometimes you have to let the wetland develop. It's got to self-select, self-organize from front to back end, and that can take some time sometimes. If it's just total suspended solids, just stuff like flock, things moving through the boxes, that'll start happening immediately. But even it will get better as all that suspended solids are being captured in the box. Now that's increasing surface area within the box. Increasing surface area increases your overall ability to catch things, but it also increases your BOD COD load. So you got to start looking at, all right, when does a certain cell have too much material in it that it's no longer working anymore? And what it actually does is, when that's the case, where there's back pressure, it starts increasing the water level above, but that's where we build an auto siphon. So as soon as it goes up, bam, and it's like a toilet and flushes itself out, and then it comes back up again, until then it restabilizes. And then over time, it slowly starts backing itself up again, and then it'll go like that again, over and over. And then we've got a little clicker, kind of like people coming into a building, how many times did it flush? And that way, like, all right, that one went 100 times. The one right below it only went 5. What's going on with this one? So it gives you an opportunity to, see where some issues are. Is like, what's the material coming out in that particular unit? Why is it doing that? Where's the hang up? Yeah. Okay. So I didn't get around to putting in another cell or for the paraterraforming, but I think I kind of covered it there in one of these here. Kind of in one of these guys. So I'm not going to really go back into it, because the only difference between paraterraforming and these smaller systems is just scale. Just way, 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 way bigger. So I guess actually oh, hey, hi Mario, thanks for joining us there. I didn't know anybody else popped on. Pleasure to have you. So Stelly, that's all I had. How we okay, it took an hour. Yeah. Questions?
Well, and first off, I just want to say that was a wonderful presentation, Colin. I felt like you really captured how integral water systems are to so many of the different areas of colonization of new planets, but also just when you're looking at these systems for terrestrial applications, how when you start looking at what you can do with these systems and what other uses can come out of them, how there's a very integrated and holistic approach to where these can be applied.
Yeah, zinc smelting.
Yeah.
Copper, that's all in solution, and that's all coming from heap leach process, and then electrowinning. We have that's been around for 150 years. Chloralkali process. That's how we get salt. I mean, this is old tech. I mean, we don't have to reinvent the wheel.
Even the stuff that's as simple as, removing a lot of the heavy acid used from iron refining, that can be a hugely greening process, which is instrumental to making these things more robust and stable, not just here, but elsewhere.
Absolutely.
So I did want to note too, you mentioned the you mentioned the minimum pressure for plants. So
yes.
Plants actually operate at the Armstrong limit as their minimum pressure. And so this is something that is more due to the physical state of water, in that below the Armstrong limit, water will not remain a liquid. So it becomes impossible for the plants to function adequately there because they're essentially exposed to vacuum. But that is
Oh, okay.
roughly 6 kilopascals, so that's about 6% of normal atmospheric pressure.